Well, in this portion, we'll look at the single slit Fraunhofer diffraction, and I'll need to explain this. It's essentially a finite width slit, but the diffraction, Fraunhofer diffraction, tells us something about the source and the detector distances. So let's look at a single slit. Now, I'm not thinking of a single slit now as just letting through one point of light, but as a broad, wide slit. I say broad, it's probably a few tenths or hundredths of micron for B. And again, remember the way we look at it is we're looking from the top down onto the slit. The slit is vertical, so a view from the top looks like this with the slit width I've chosen as B. And we impinge on this plane waves exactly perpendicular. The wave fronts are exactly parallel to the plate that has the slit in it. Okay? And so we have that. And what that entails, particularly in the early days, to get this, you had to have produce a point source of light or something approximating a point source. And so that would be spherical wavelets. But the source of light had to be far enough away so that by the time it gets over to the slit, they are plane wave. The plane wave approximation is good. And so one aspect of Fraunhofer diffraction approximation is that the source of the light has to be far away in that sense. By the time it hits here, they're plane waves. Okay? The way I've got it tried to draw it aligned is I put the origin to my coordinate system, which I call y prime in this direction, and this should be right down the center, is right down the center of the slit. Okay? So I center it up, and then I know that I can decompose this wave that is in here as a bunch of point sources that emanate spherical wavelets by Huygens principle. And then ultimately I'll try to add all those up over here at my detector, which could be the eye, but nowadays as often as not would be a photo detector of some sort over here. That I have set up so that it can rotate at a radius x around this, so x is always positive, and collect the intensity information from all of the light that gets over to here. So x is that distance from the center to the detector. Theta is the angle it makes with the straight bisector of the slit. And now then I focus on just the light that comes into this portion here that's of thickness dy prime, and I've got it located at y prime. And that, as I've said, emanates by Huygens principle, a spherical wavelet. Any wavefront can be considered to be made up of a bunch of spherical point sources that emanate spherical wavelets, and then the ultimate wave that gets to a point is a superposition of all of these spherical wavelets from every point on that wavefront. And that leads us to another thing. By the time they get to the detector, I want this distance x to be far enough away so that they start off as spherical waves, by the time they get here, they're plane waves. And that's the other half of Fraunhofer diffraction patterns, is that one assumes that not only the source is a long distance away from the slit, but also the detector is a long distance away from the slit, in the sense that it's many wavelengths away. Now, typically, in the early days, this x might be 10 centimeters or so, and the source might be a similar distance, 10 centimeters, and then the wavelengths of light, they might be 550 nanometers. So there's many wavelengths, and so the typical setup in a laboratory setting would be in this Fraunhofer approximation regime, which I've described here. Well, now I can focus here and get the spherical wavelet for just this piece. Uh, so I assume that it has some amplitude here, and whatever the amount of wave that's in this is proportional to the thickness dy prime. And it's located at a point y prime. In this case, y prime would be negative. It's below the axis, but that's kind of immaterial for us, as we'll see. The distance that it travels from this point over to here, I've labeled as x prime. And it's slightly different than x. Yeah? If you think of this now as a center, then I could swing out an arc here, and if I'm far enough away, that arc length is essentially this leg here, and it's perpendicular to both of these radii. And from that you can see that x prime, the total distance from the point source to P, and x, well, x prime is from here on out, and so, x prime is equal to x plus delta. X prime is the total distance, and from here on out is x, because it's an equilateral, or an arc length of a circle. And so x prime is equal to x plus delta. You can also probably tell, it's a little easier for me to see on this one now for some reason, that this angle theta, if this angle is 90, then this is 90 minus theta, but this is a right angle here, and so this angle is theta. So we have this little right triangle, delta on one side, the hypotenuse is over here, which is y prime, and the angle is theta. That is this angle of this little triangle here, this apex angle. And so the sine of theta is delta over y prime, and delta is y prime times the sine of theta. So we can get that distance. And then we're pretty well all set. We just write the spherical wavelet formula. It's true in general, but in particular it's true by the time you're over here at x prime. It's the amplitude, which is proportional to dy prime, how much light is coming through there. E naught we can think of as just a proportionality constant related to the amplitude that's going through. X prime is the distance r, yeah, and x prime is the total distance r from the spherical wavelet to this point. So by the time it gets over here, it really is a spherical wavelet. I used sine, could have used cosine. And now I'm going to turn that into a complex wave just by assuming that we can use the Euler relationship, and if we need to go back to the real, we can take the imaginary part, but we won't need to. So really get the complex a spherical wavelet form in this fashion, where x prime is the distance r from the source of the spherical wavelet, point source of the spherical wavelet. And now then, we recognize that x prime is equal to x plus delta. Up above. And I just plug that in for x prime in both cases, here and here. I'll first work on the exponential part, but I separate out the plane wave portion, ikx minus omega t. And there's also an ik delta, which I separate in this form. It's really a phase shift that occurs. And then also, I recognize the fact that x is probably 10 centimeters at a minimum, and delta is maybe something on the 100th of a micron, and so there's a factor of 10 to the 7th or 8th here. So as long as you're not measuring things out to 9 or 10 decimal places, we'll, to a very, very good approximation, x plus delta is the same as x. So there's an approximation. All really plane wave, same, no less or more than assuming that Fraunhofer regime. We're out far enough to get plane waves. And you can see the plane wave. I mean, this is just the form. All this other stuff, E naught and X are constants. The delta is just a phase factor, and so this portion here is just a plane wave portion. However, it's only due to this one piece, and I now need to add up all of them due to all of these pieces from minus y prime equal minus b over 2 to b over 2 to get the total wave that hits over here at b. So because of this, the phase factors, some will be in phase and out of phase, and so you can get some constructive and destructive interference in general. Well, add them all up. That means sum them all up. I put in what delta is y prime sine theta. And a superposition principle for a continuous situation is just, instead of a summation, it's an integral from minus y prime equal minus b over 2 to b over 2 of all of this up here. So add up all the dE's due to all of those spherical wavelets that go through the slit. Oh, there's lots of stuff that can be pulled outside. E naught and x, and this plane wave here can all be pulled out. They don't depend on y prime, which is the integration variable. The integration is then simply of this function, and that's pretty easy because it's really just an integral of e to a constant times y prime, and the integral of an exponential is just the exponential divided by the argument, the constant a that's multiplying it in the exponent, which in our case is ik sine theta. And then I evaluate that on the two endpoints, minus b prime and b, y prime equal to minus b over 2 and y prime equal to b over 2. So plugging those in, the upper limit, I get this term. The lower limit, I just get the negative of it. And all of that over ik sine theta. And you might already have seen that this is very much like a sine, or part of a sine. And so I lump those together. I take the I here and move it dividing underneath them. I multiply by 2 and divide by 2 so that I get this whole term here as a sine function. And then I notice also that this the I I've gotten rid of, it's over here, so I get k sine theta. And that's very nearly the argument of this sine function that we're going to wind up with. The only difference is I need a b over 2, so I multiply the top by b over 2 and the denominator by b over 2. So I do that in the denominator, I keep here. And then the b over 2 is up in the numerator, and that'll cancel out this 2. And so it simply becomes this expression. And then I've got sine of beta divided by beta, where I've defined beta to be kb over 2 sine theta, which is just the argument of this sine here. And you may recognize that. That's just the sinc function, sometimes called the sinc function. So I've got the total field at that point. And then to get the irradiance, or the time average value of intensity, I use our formula derived earlier, 1/2 epsilon naught c times the absolute modulus of that field squared. And this, of course, is just the electric field complex conjugated times the electric field back again and give me that absolute modulus. These two, the complex conjugate just says substitute everywhere there's an I and minus I, so the only thing it changes is I get a minus I here, which will multiply to the plus I to make that imaginary part go away. And everything else is just multiplied together. B times B is B squared, E naught times E naught is E naught squared, X times X is X squared, sine beta over beta is sine squared beta over beta squared. Then you'll notice that all of this, these are just constants for our setup here. E naught is a measure of how bright the source is. And a brighter source has a brighter value, larger value of E naught and of E, and so this would be brighter. The dimmer it is, the smaller it is. X is a constant for our detector that's rotating around that central point, so it's always the same. And so all of this is just a bunch of constants for a given situation. And I lump all those into one lumped constant of I naught. Doesn't change for a given experimental situation. and I get the final value for our intensity, or the irradiance as it's sometimes called, time average value of the intensity. It goes like I naught times the square of the sinc function. Remember, beta is kb over 2 sine theta. We can look at the case where beta is equal to 0. And if beta is equal to 0, k and b and 2 are all non-zero. And so that says the sine of theta has to be equal to 0, which also gives us theta equals 0. So really, at theta equals 0, beta becomes 0. It's probably a better way to look at it. But what happens to sine beta over beta as beta is 0? Well, if you look at that, as beta goes to 0, this becomes indeterminate. It becomes a 0 over 0. And so I can use L'Hopital's rule to take that limit. Derivative of sine is cosine. And derivative of the denominator, beta is 1. And then take the limit, and you find that this sine beta over beta, as beta goes to 0, really is 1. So at theta equals 0, this goes to beta equals 0, which goes to 1. And so I naught, and if you look at that, that's the constant that's out front at theta equals 0. In fact, it becomes a maximum, as we'll see. That occurs at theta equals 0. We can look for minima. Minima occur for I when that sine beta over beta squared is 0, which only occurs if sine beta over beta is 0. If you look at the minima, it should be pretty clear. I've got a squared quantity here, and so the minima for a squared quantity is going to be, the radiance is always a positive quantity, and so the minimum is actually 0. But that occurs when sine beta over beta is 0. Now I know that beta equal to 0 is not, this is not 0. It's in fact 1. So that would give us an intensity of I naught. And so the minima are really here. So beta is not 0, and so this will vanish when sine beta is equal to 0. Now, in general, the sign vanishes for beta equal to 0 or any integer multiple of pi, positive or negative or 0. But we already know that for beta equals 0, I is not 0, it's I naught, so we have to eliminate that one. Or more succinctly, beta is equal to m times pi, where m could be plus or minus 1, plus or minus 2. Beta is k b over 2 sine theta. K is 2 pi over lambda times b over 2 sine theta is equal to m pi for the minimum condition. And we get a fair amount of cancellation. The pi's will cancel, the 2's will cancel. And if I bring the lambda over here, we get the angles at which we achieve minimal intensity. In fact, it's 0 if you look at it. That sign vanishes, so we get 0 intensity for b equal to sine theta m. M labels this value m here, so I get a whole bunch of relative minima, all where I is equal to 0 at these integer multiples of lambda. With the exception of m equal to 0, where it's a maximum, as we see. On the other hand, we can look for maxima. And the maxima, if you go back and look at our original formula, if I want to maximize this, then the derivative with respect to beta has to vanish at a relative maximum. And so that entails well, it would have been an I naught here, but I've already divided that out, that this derivative of sinc function squared has to vanish, or the derivative of sine squared beta over beta squared has to equal 0. And we can do that differentiation. The derivative of the numerator is 2 sine beta cosine beta over beta squared. plus sine squared beta times the derivative of 1 over beta squared, which is minus 2 beta cubed. So we get that. And we get some cancellation. The 2's will divide out. I get a sign here that will cancel one of these, so I'm still left with a sign. And then a beta squared here will cancel 2 of these powers, so I'm still left with a beta over here. And so on this side I get cosine beta, and over here I get the sine over beta, which I take over to the other side. And so whenever this equation, if I divide by cosine and multiply by beta, I get whenever beta is equal to the tangent of beta, then we will satisfy this condition and be at a relative maximum. And the way I do that is you have to ultimately do it numerically if you want great precision, but a good way to look at it is to first plot the tangent of beta, and that's these S-like curves. Remember, the tangents blow up. They go asymptotic at pi over 2 and minus pi over 2, and then subsequent branches you get that the asymptotes as well. I didn't draw the negative sides, but it's kind of the same. And let's so I plot the tangent, and that's these S-shaped curves, and then I plot a beta as a function of beta, which is just a straight line. And then everywhere they cross gives me a relative maximum. And as you'll see, if you look at these, they cross very, very close to 3 pi over 2 is the first one. It's a little bit under that for this one here. Really not the first one, but for one of them. The next one is beta, very, very close, even closer to 5 pi over 2. And it gets closer the larger the beta gets in these things. So essentially the crossings are at 3 pi over 2, 5 pi over 2 for beta. We need to examine this portion a little bit closer, and if you do that, you can expand the tangent side in this form. There's a Taylor series expansion. The leading order is beta, but the next term is beta cubed over 3. In fact, all of the subsequent terms in the Taylor series are all positive. And so for this region here, if we blow that up, we get the tangent something like this, and the straight line portion, but the tangent is always above the line beta equal to beta, or y equal to beta. And so this is always above, and so the crossing really is at beta equal to 0 here. Now, if you like, you can call that beta 1 for the crossing here, but in point of fact, we've already gotten that one, so we know that when beta is equal to 0, that 0 crossing, we have I naught as the intensity, and so it's a relative maximum as well. In fact, it's the absolute maximum. So first beta is beta equals 0. The second one is close to 3 halves pi. The third one is close to 5 halves pi. And you have a symmetric thing on the other side. So to good approximation, for large beta, you get maxima at beta plus or minus 3 pi plus or minus 5 pi over 2, and beta equals 0, but that would fall out of this pattern here. These odd numbers can be represented as 2m plus 1. That's 3, 5, so I'll put in a 1 here, you get 3 pi over 2. You put a 2 here, you'll get 5. And beta is still k b over 2 sine theta, and that will give me the condition whenever beta is equal to that, I get a relative maximum. K is 2 pi over lambda, b over 2 sine theta. Again, you get a cancellation of pi's, and then these 2's cancel. And you can multiply lambda across is the way it's usually shown. And then usually they go ahead and divide this out, so you get m plus a half lambda. And you get relative maxima at these expressions here. When m is not 0, you actually, so if I put a 0 here, I'd get plus or minus a half over here. But that one doesn't occur, because reasons we've shown. And so it's really plus or minus 1, plus or minus 2. Now, there is a relative maximum at 0, but we handled that was the first case that we considered. And it's actually the absolute maximum, which is I0. So if you put all that together, you get a sinc function that looks something like this, or a sinc function squared, actually. You have the absolute maximum as at beta equals 0. It falls off at pi, it's 0. In fact, any multiple of pi on either side, it goes to 0. And then the next relative maximum occurs at plus 1 or minus 1. That's here. And that's very, very nearly 3 pi over 2 at beta equals 3 pi over 2. It's a little bit under, but it's so close it's usually not worth going after any closer. The next one up here is when m is equal to 2 in this formula. So you get 5 pi over 2. And they continue to fall off. For this m equal to 1 maximum, or the m equal to minus 1, it's really the same thing. I over I0 is this. But here beta at the maximum is close to, so this is approximate, sine of 3 pi over 2 over 3 pi over 2 squared. Well, at sine of 3 pi over 2 is really minus 1, but you square it, it simply becomes 1. And this becomes the 2 squared becomes 4, and then you get 9 pi squared on the bottom. And when you work that out, you get essentially about 0.04. So by the time, if this starts off at I0, this one, the height here, the intensity at this relative maxima is about 4.5% of I0, so 0.045. The next one is even further down. At this one, you're now at roughly, again, it's an approximation, because it's just inside this 5 pi over 2, but if I plug that in for beta, 5 pi over 2 is 1, I believe, either plus or minus 1. When you square it, it becomes 1. And this becomes 4 over 25 pi squared. When I calculated that, that's about 1.6%. So this one's even smaller. So by far, most of the intensity is in this central Bowles region, and it falls off very precipitously for these subsequent relative maxima. And that's the diffraction pattern for a single slit in the Fraunhofer regime.